In the deep quiet of the night sky, when most of the world was asleep, a small telescope in a modest German backyard picked up a change that would not stay small for long. Maria Schultz, an amateur astronomer who loved the steady ritual of checking the heavens, watched her screen blink with numbers she had seen 1,000 times before. She had trained her 12-inch on the Interstellar visitor catalogued as 3I/ATLAS, a traveler from beyond the sun that had passed into human attention months earlier. It had behaved like other strange visitors, odd, slightly unpredictable, but not hostile, not urgent. Then, in a single watchful sweep, the readout of brightness jumped. The change was enormous for something in deep space, a sudden rise equivalent to about 1.4 magnitudes. The light leveled off at the higher value and held there for 6 full minutes. Maria thought at first it had to be a software error. She double-checked her calibration stars. She reran the data against atmospheric logs. Everything matched. Her instruments were fine. The anomaly was real. She posted a short note to a local forum and set the recording to public. Within 30 minutes, other observers thousands of kilometers away began posting their own charts. A New Zealand backyard scope, a university telescope in Arizona, an enthusiast in Brazil. Each light curve matched the same strange shape, a flat, steady source that suddenly, like a heartbeat, jumped and stayed bright. The stories came in rapidly. An amateur in Chile shared a recording. A robotic survey telescope on Maui confirmed a perfect spike. It was as if the object had been asleep and then, in a tiny human fraction of time, had decided to shine. News moved across the web like wildfire. The hashtag at LAS Anomaly trended within hours. Citizen science platforms lit up. Groups of volunteers compared timestamps, exposures, and calibration images. The consensus grew impossibly fast. This was not a data glitch, not a coordinated hoax, and not an atmospheric flare. It was a real, literal flash in space, and it had happened with machine precision across the planet. Amateur networks, normally content to trade images and gossip over forums, suddenly looked like the first responders of a global scientific emergency. By dawn in Europe, professional observatories were awake. Survey telescopes that had been monitoring asteroids for years reported the same spike. Pan-STARRS and other wide-field programs logged measurements that matched the amateur charts down to the second. Then the decision came to escalate. The Deep Space Network, the infrastructure that keeps track of spacecraft moving between worlds, made an extraordinary choice. Engineers voted, quickly and with a gravity rarely seen outside crisis rooms, to redirect one of the big 70-meter dishes away from its scheduled Mars telemetry. For nearly a day, those powerful antennas would be used to ping a single point in deep space and listen for echoes. The move was not taken lightly. The usual trade-offs, lost telemetry from Mars missions, postponed data from probes already stretched thin, were measured in dozens of man-hours and millions of dollars. But humanity's instruments had whispered about something unusual. The whisper had multiplied into a shout. The deep anxiety in control rooms was not that an asteroid was on a collision course. It was that an unknown visitor seemed to be doing things that no natural object should do. The spike in brightness was only the beginning. Within the next 24 hours, the global telescope community came together in ways that surprised many. Time on the Very Large Telescope in Chile, Gemini North in Hawaii, and observatories in Japan was reallocated. The massive Chinese Fast Radio Telescope joined the chorus. Even space-based assets were pointed, retargeted, and tasked. The International Astronomical Union called an emergency session, a public announcement that only rarely appears on calendars. Debate flared over the right word to use. Comet, asteroid, interstellar debris. The official designation quietly shifted from 3I/ATLASC/2025 R2 to something less committed, the 3I/ATLAS complex. The term complex acknowledged an uncomfortable possibility that this thing was more than a single piece of rock following a dead track through gravity. While telescopes watched, a strange suppression of chatter set in. Discussions that had been loud and open an hour earlier fell silent. Astronomers who had been sharing live updates stopped posting. Private research channels went quiet, then locked. Social media showed a curious dip. Verified accounts associated with major observatories and scientists reduced their output by roughly 70% over the next day. That absence was not the silence of boredom. It felt like a collective intake of breath. a moment where professionals stepped back from public conversation to check their work, to verify, or perhaps to prepare for the consequences of what might follow. What trickled out of confirmed logs painted a puzzling and eerie portrait. Radar returns tuned to the object's coordinates showed evidence of non-gravitational acceleration, movement that could not be explained solely by known forces, and which appeared 4 times stronger than expected for a chunk of ice or rock. Infrared arrays recorded an excess, an energy plateau roughly 30 Kelvin hotter than predicted, not consistent with reflected sunlight. Gamma-ray monitors noted faint, intermittent bursts keyed to the same patch of sky. Those were not coincidences. Instruments thousands of kilometers apart, measuring different parts of the spectrum, pointed to a single truth. Something active was happening with 3I/ATLAS. Then James Webb, with its cold mirrors and keen infrared eye, added another twist. Webb's differential imaging revealed a faint secondary source perfectly aligned with the primary body and holding a fixed separation of about 120 kilometers. At first glance, the team presumed the second object was debris or a fragment, a natural satellite torn off in some long-ago collision. But further observations showed behavior no fragment should sustain. The 2 bodies maintained exact synchronization. They orbited an invisible common point, as if guided, not by chance gravity, but by a precise choreography. Gravity, the team realized, could not easily explain their tight, stable companionship. The second body showed almost no reflected light, black in a visual sense, but it emitted faint microwave radiation consistent with controlled heat dissipation, a signature that smelled not of random thermal emission but of active regulation, as if whatever inhabited that fragment were purposefully managing its temperature. Language began to change in the communications among observatories. Where once scientists spoke with safe, cautious terms, they started dropping phrases like geometric edges, internal luminescence, and directed emission. Webb's images showed diffractive spikes that matched the patterns produced by sharp edges and clean faces. It no longer looked like a pile of rubble. The object appeared to be unfolding or rearranging itself. Spectrographic readings suggested that some energy was moving inward. Temperatures in certain bands dropped by roughly 60 Kelvin even as other wavelengths lit up, a behavior consistent with internal systems drawing in power rather than a surface simply warmed by the sun. Then came the signal. For 12 seconds, a focused radio beam shot out from the exact coordinates of the complex, aimed with a precision that left radio engineers speechless. The beam was narrow, it was structured, it carried patterns and a harmonic balance that suggested intentional order rather than random astrophysical noise. Instruments across continents recorded the pulse. The world heard, in instrument readings at least, the same brief breath of information. For many, the beam's brevity only intensified its strangeness, a short, precise handshake sent across hundreds of millions of kilometers and then gone. The square-kilometer array, with its massive field and immense sensitivity, reconstructed the waveform. The team's analysis unveiled a built-in rhythm. The 12-second burst nested a recurring 247-second pulse that had by then become well known among researchers who had been watching the object for weeks. Embedded in the signal were frequency ratios that matched the spectral lines of hydrogen, the same lines that, in physics classrooms and radio labs across the world, are taught as the universal frequencies any technologically aware species would likely know. Choosing hydrogen frequencies is a deliberate act. Hydrogen is the universe's most common atom, and its spectrum is a natural position for cosmic communication attempts. Whatever generated the beam had chosen that universal alphabet. Even more staggering was what the waveform looked like when converted into a visual representation. Rendered as a spectrogram, the 12-second transmission drew a repeating geometric figure, 6 perfect hexagons spiraling outward from a central point. It mirrored the diffraction images Webb had recorded. When teams translated the pattern into a 3-dimensional blueprint, it matched an orbital architecture with uncanny parallels to a planetary system. Resonance points arrayed like notes on a musical scale. The mapping suggested a design that echoed gravitational harmony, yet the chart's center was empty. The pattern placed an empty void at the heart, where a star should sit. The void corresponded precisely with the region of space where 3I/ATLAS now drifted. Debate among scientists became a quiet war of interpretation. Some argued that humans are pattern-seeking animals and that the brain naturally imposes order where none exists. Pareidolia, they warned, humans seeing faces in clouds. Others, more cautious and in smaller voices, proposed a more radical idea. The signal was not simply a message, it was a tuning note. Avi Loeb, one of the astrophysicists who wrote quickly and cautiously about resonant structures, suggested that the broadcast had the character of a calibration sequence rather than content meant to convey language. Like a musician playing a single tone to tune an instrument, the object might be checking the gravitational and electromagnetic pitch of the solar system, synchronizing itself to Earth's orbital rhythm. If so, the 12-second beam was the test tone before a real transmission. Those interpretations only hardened the feeling among mission planners that this was no ordinary celestial event. Magnetometers registered a shift 12 seconds after the beam faded. Earth's ionospheric resonance, the background hum, sometimes called the Schumann frequency, nudged by roughly 0.02 Hz. The change was tiny, almost laughably so to a layperson, but significant in a discipline where tiny differences speak loudly. It meant that the pulse had not simply been received by telescopes, it had interacted with the planet itself. The idea that a beam from an interstellar object could alter the electromagnetic heartbeat of Earth, even briefly, moved the event from the category of interesting anomaly to the realm of direct interaction. Public statements were carefully crafted and, from the outside, evasive. Agencies released bland reassurances about data verification, calibration checks, and the need for peer review. Meanwhile, an internal task force, some called it Project Helios, ran simulations and cross-checked every recorded photon. Their private conclusion, one not shared in press conferences, was unsettling. The 12-second beam had been a response, not the initial provocation. The initial brightness spike, now referred to in some internal notes as the first flare, had radiated thousands of faint electromagnetic signatures. From amateur instruments, from survey telescopes, from consumer satellites and radar systems. Those emissions had, in effect, illuminated the object. The visitor had returned illumination with a focused, structured emission aimed back at the source region. In other words, 3I/ATLAS had answered back. What the task force could not say publicly was this: the response was not a random reflection. It had chosen a carrier, the hydrogen line frequencies, that would make sense to any civilization with radio astronomy. Moreover, the waveform's geometry didn't look accidental. When teams overlaid the pattern on the object's image, the hexagonal structure corresponded to the spatial arrangement of the two bodies and their surrounding halo. It was, in the cold engineering language of the field, a blueprint broadcast back toward the sending engines, perhaps to say, "I am here. I have matched your pitch." The secrecy that followed the discovery changed the tone of scientific discourse. Papers that should have been rushed to preprint servers sat in draft folders. Observatories that had once tweeted frequent updates now published scheduled, heavily edited releases. Leaks from inside the networks were rare, and those that did appear were quickly traced and removed. For many, the containment felt necessary, a way to prevent sensationalism and misinterpretation. For others, it smacked of something more protective, the sense that with each additional public word, the risk of panic or misread reaction increased. As the event unfolded, human narratives began to thread through the technical logs. Maria Schultz, who had started the chain of detection from her backyard, found herself in the eye of a storm she had never asked for. Journalists called, colleagues reached out, but Maria's earliest reaction was simply wonder. She had become part of a global orchestra, a single point in a chorus of instruments that collectively noticed something no single tool could have. She felt the weight of that responsibility, and the thrill of being the first to voice a question none of them were prepared to answer. On the observational side, the satellites that had been repurposed to study the object returned more puzzling data. Infrared cameras on Mars orbiters, having burned fuel and shifted schedule to point toward the unknown, recorded the same temperature anomaly that Earth telescopes recorded. That confirmed it was not the result of local instrument error or Earth's atmosphere. Even from millions of kilometers away, the signals agreed. Ground-based radar seemed to detect echoes that suggested non-standard reflection properties. The object did not scatter radio signals like rough ice or rock. Instead, there seemed to be angularly dependent echoes. Some transmissions bounced back stronger at particular angles, hinting at structured surfaces or perhaps active antennae. And during the period the object was closest to the ecliptic, a faint halo bloomed around it, visible even to skilled amateurs with mid-sized telescopes. The halo glowed not with reflected sunlight, but with a soft internal luminescence. People who had never been interested in astronomy found themselves looking up. Smartphone cameras pointed at the same spot that scientists stared at with cooled CCDs and multi-million-dollar mirrors. The public conversation mixed excitement with fear. Social media held its breath, as much for spectacle as for the unknown. Conspiracy theorists and earnest commenters rushed to claim ownership of the narrative. Governments deliberated quietly. Emergency management agencies held tabletop exercises to decide what would happen if, someday, the mystery moved from observation to action. Yet after a few days of intense observations, the object quieted. It ceased the bright emission, slowed its non-gravitational acceleration, and its infrared excess vanished. The transient gamma bursts stopped. The radio beam never repeated. The complex drifted outward beyond the orbit of Mars like an unhurried traveler resuming a long journey. The radio community's last loud keystrokes fell into silence as engineers and astronomers tried to make meaning of an event that had both revealed and concealed itself. Even in the aftermath, fragments of data intrigued and haunted specialists. Analysts who worked on the waveform found a repeating motif echoing the 247-second pulse detected earlier. That pulse had been a ghost in the monitoring systems for weeks, a low-amplitude periodicity that only the most patient signal processors had noticed. The 12-second beam had nested that same pulse inside higher-order harmonics. Whether that was an attempt to amplify a detection signature or to punctuate meaning with a pattern familiar to the sender, no one could say with confidence. Philosophers and sociologists watched the scientific community's behavior with equal fascination. The way institutions moved from openness to caution, the way secrecy pooled around uncertain knowledge, revealed cultural habits about how humanity handles the truly new. Some argued the decision to withhold partial findings was responsible. Others said transparency would have kept public trust higher. But almost everyone agreed on one point. The event had changed the way humanity thought about objects from beyond the solar system. These interstellar visitors were no longer mindless rocks. At least one had shown signs of whatever could be called agency, responses, regulation, emission. In private, scientists debated the range of plausible explanations with the sort of rigorous imagination that keeps the discipline honest. Could a natural process produce a controlled microwave emission? Could complex organic chemistry, under unusual environmental stress, produce rapid brightening and then sustain it? Could an unknown electrostatic or plasma effect in the interstellar medium create a false impression of an engineered phenomenon? Those were intellectually fair questions, but the geometry, the regulated microwave dissipation, the synchronized companion body, those factors made purely natural accounts feel like misfits pressed into a mold. The possibility that it was a probe, a construct deliberately crossing the void, became a topic treated with the same caution one might use to discuss a scientific hypothesis that carries outsized cultural weight. Suddenly, mundane procedural concerns took on new meaning. Would a broadcast from a foreign construct be an invitation, a test, or a warning? Could an interaction disturb delicate Earth systems? Scientists were careful to remind each other and the public that contact does not imply malicious intent, but neither did they assume benevolence. The unknown required measured humility. The secrecy and silence around the event, however, also sparked a small, determined wave of citizen science. Amateur programmers wrote software to sift public telemetry for echoes. Independent radio hobbyists tuned sensitive receivers, hoping for a repeat signal. Hackers in university labs tried to model how a small object could sustain a regulated temperature in the cold of space. The internet, with its combustible mix of curiosity and ingenuity, refused to be quiet. People with a passion for discovery insisted that whatever truth the institutions held should not be the sole property of a few committees. Months later, when academic papers finally began to appear, they did so with nuance and caution. Teams published results that carefully weighed observational constraints against theoretical models. Some offered conservative reconstructions that favored exotic natural explanations. Others, more speculative, presented the full range of evidence and allowed for the remote possibility that a construct, not necessarily alien in the way pop culture imagines, but an artifact with designed features, could fit more of the oddities than any single natural model. No consensus emerged. The scientific community, built to iterate and refine, found itself both excited and unnerved. And the core question remained, why had the object sent a beam aimed at Earth's ecliptic, at a place where human instruments clustered? If the beam had been a handshake, it had been a short and precise one. If it had been a tuning note, the test appeared successful. Earth's systems had registered the pulse. The object had touched the planet's electromagnetic field. Whether that touch meant more, whether it opened a channel, wrote a set of instructions, or merely confirmed a resonance, was not yet known. Among the scientists who had worked closest to the data, many felt a subtle shift in their worldview. The universe, once largely a backdrop of physics to observe, seemed in that moment to have reached back. Even those who insisted on natural processes admitted that the three-eye atlas complex forced them to expand their categories of what celestial phenomena might look like. Maria Schultz, sitting at her modest desk in Germany and watching her name appear in footnotes of formal papers, sometimes thought about the bewildering chain that started with her telescope and her quiet decision to post a graph. She remembered the momentary thrill and the dread that followed when the world stopped publishing its thoughts. Humanity found itself in a new posture, simultaneously smaller and larger. Smaller because a stranger from another star system had decided, for reasons unknown, to make a brief, structured contact with Earth. Larger because the global scientific apparatus, the network stitched together by amateurs, institutions, and space agencies, had organized a response that would have been impossible a century ago. The act of coordinated looking had become a kind of collective intelligence, a way to notice and to respond to a universe that does not always announce its intentions politely. The 3I/ATLAS complex moved on, carrying the secrets it had displayed and withholding many others. It left behind data, treasure troves of puzzling facts that would occupy instrument teams for years. It left behind a new protocol for how the world might respond to future oddities, rapid coordination, a cautious public face, and the recognition that sometimes scientific curiosity must be balanced with the care to avoid premature conclusions. And for those who had stared longest at the patterns, who had run the numbers at 3 in the morning and adjusted calibration stars until their eyes blurred, a quieter question remained. If the object had come to synchronize, to tune, or to test, what came next? Would another signal return? If so, what form would it take? Would it speak in mathematics, in physical configurations, in carefully nested frequencies built on atomic constants? Would it be simple, aimed at establishing contact, or complex, a demonstration of engineering and thought? Scientists who had once believed that the universe kept to an impersonal script found their imaginations widened. The 3I/ATLAS complex did not offer grand proclamations or sweeping messages. It performed a brief, precise act, yet that small act tightened the knot of human curiosity and fear in ways that would not unknot easily. For some, it was a hopeful sign that the cosmos contained others who could, in some sense, notice and respond. For others, it was a warning that human beings now lived in a universe where the quiet could crack open at any second and reveal something profoundly new. In the end, the complex's appearance and its 12-second pulse became a hinge in modern observational history. It reminded the world that the skies are not static and that the universe remains in equal parts stranger and more inviting than people allow themselves to imagine. Observatories returned to their normal schedules. Engineers rebalanced mission plans that had been postponed. Funding committees revised proposals. Scholarly debates churned slowly and diligently. But the memory of those 12 seconds, of the hexagonal pattern rendered on a spectrogram, of the faint pulse nudging Earth's ionosphere, it would not fade. When people looked up now, the night had a different taste. The stars sat where they always had, patient and distant. Yet there was a new awareness that an object from beyond the sun could slip into the sky, do something inexplicable for a short, tight time, and then continue on its lonely road. Whether 3I/ATLAS had come to study, to test, or to communicate was still an open question. Scientists made plans, retooled arrays, and drafted protocols for what to do if the pulse returned. The world kept its telescopes warm, and somewhere in a small suburb of Germany, Maria still took occasional photographs of the sky, checking calibration stars and logging her measurements. She had not expected fame or a crisis. She had only hoped to observe. But in her quiet persistence, she had helped the world notice something that mattered. The rest of humanity had learned to notice more carefully too, to be ready when the night decides, in a single precise breath, to speak back.